Hello everyone, this is Kay Styles and I'll be talking about frequency hopping for my communications presentation. So to begin, just a quick overview of what this presentation will talk about. First, I'll kind of discuss a broad general overview of what frequency hopping is. Then I'll move into its history, so kind of the early sides of frequency hopping, and then move into what I like to call the basis for the future, which is a patent that is kind of regarded as really the beginnings of what modern frequency hopping is. Then I'll move into how frequency hopping works, which includes channels, how the transmitter and receiver specifically works, the advantages to using frequency hopping, and the disadvantages to using frequency hopping. Then lastly, I'll talk about Bluetooth application because Bluetooth actually involves frequency hopping for how it works. So to start, what is frequency hopping? So frequency hopping is a spread spectrum technique. This is basically methods where a signal is deliberately spread across a frequency domain. And there are really three advantages for using this method versus something like the fixed frequency transmission, because you're going to get more resistance to interference, it will be more difficult to intercept the signal, and you'll be able to share frequency band with minimal interference. And I'll talk a little more specifically later about how frequency hopping, about the specifics of how frequency hopping has those advantages. Moving on to the actual definition of frequency hopping. So frequency hopping is a method of transmitting audio signals by shifting carriers across numerous channels. So this is done using a pseudo-random sequence that is known by the sender and the receiver, and that's a really important part of frequency hopping that I'll discuss a little more later. Then frequency hopping is also defined in the unregulated 2.4 gigahertz band. So this band has kind of been left open for wireless products and Bluetooth and items that would use frequency hopping. So the history, so early frequency hopping. So it kind of started, frequency hopping idea kind of started in Tesla's 1903 patent called Methods of Signaling. Although the patent doesn't ever specifically mention the phrase frequency hopping, it definitely alludes to it in its discussion of the system. So the system he describes is a system that would keep signals safe from being interfered with or being intercepted or disturbed or jammed. So really, although he didn't mention frequency hopping, he was talking about what would eventually become frequency hopping. Frequency hopping was also used by Germany in 1950 for their military uses. So they had a primitive frequency hopping radio that they would use to stop the British from eavesdropping on their communications. So that was kind of the early part of frequency hopping, but it is really this 1942 patent that is referenced a lot for the modern day frequency hopping. So this was created by Heidi Lamar and George Antheil, and quick fun fact about them, Heidi was actually a Hollywood actress and George was a pianist and Hollywood producer. So I think it's pretty cool that they created something that affects our modern technology so much. So in their 1942 patent called the Secret Communications System, they discuss frequency hopping in regards to torpedo control. So they wanted to use frequency hopping to prevent the controller's transmission from being jammed in any way. Unfortunately, this concept was not picked up by the military at that time. George used a piano as like an example of how to explain their concept, and the military apparently thought that that meant that a piano needed to be in the device, and so they didn't pick it up then, but it was picked up in the 1960s by the military for use in secure communications. There was a difference though, because the originally proposed patent was a mechanical system. As you can see, if you look in the picture to the right, that is the actual patent and system that they designed. but when it was adapted in the 1960s, it was adapted in an electrical system. So like I said, this was kind of the kickstart, or what is referenced a lot for how modern frequency hopping works today, and it's referenced in a lot of modern patents. So moving on from history, we'll move into how frequency hopping actually works. So an important first part to know about frequency hopping is about the channels. So frequency hopping works by quote-unquote hopping signals from different channels, every period or delineated amount of time. So these channels are really just divided sections of frequencies. As you can see in the picture at A with channel assignments, you can see that there are frequencies split up evenly into different channels. And really the spacing between these frequencies and the number of channels that there would be really correspond to the length of the input signal. But all the channels are divided out equally. They will all be equal length. But also for the amount 2K carrier 2 to the K carrier frequencies will also produce 2 to the K channel. So there will be a channel for every frequency depending on how it's split up. So these are the channels that the signal will hop through. So as you can see in the B part of the photo, you have these highlighted squares, and that's kind of the signal, showing you how the signal would jump through the frequencies at the delineated amount of time. And again, so in the 2.4 gigahertz band that uses frequency hopping is in, there are 79 different channels. So for how the system works, I'd actually like to start talking with the transmitter. So this is a block diagram of just a normal frequency hopping transmitter. So what's first going to happen is we'll get a modulated signal. So the modulator will produce a signal centered around some base frequency needed for whatever project is being conducted. Then that signal would get modulated with the CT signal pictured, which is the frequency of the channel that we want to hop the signal to next. So the way we get that CT is, as you can see below, is through using a pseudo-noise source, the channel table, and then a frequency synthesizer. So a pseudo-noise source, which could be a couple different things, is going to produce a new k-bit value, and that k-bit value is going to be go into the channel table, and based on that value, a certain channel will be selected. From that channel, then a frequency will be produced that, is corresponding with that channel. And that's how we get which frequency we want to next send the signal to. So that signal is modulated with the previous signal to create a signal that is centered at the next frequency that we want to send it to. Then that signal is passed through the bandpass filter, which is going to produce our final spread spectrum signal that we need. So before moving on to the receiver, there's a pretty important part of the transmitter and the receiver that we need to know. So in order for frequency hopping to work, the transmitter and the receiver must both know the pseudo-random sequence. So they need to be synchronized. So this is done by synchronizing them together on a particular channel and seed value. So something about the receiver is they contain the same pseudo-random algorithm that the transceiver contains. So the transmitter contains. So when they get synchronized on a particular channel and seed value, the receiver can take that information and use it to be able to follow the signal that is coming from the transmitter and be able to receive the signal since it's being able to follow it. So as we move on to the block diagram for the receiver, you see just that. As you can see, we're going to receive the signal, and that's going to be demodulated with the frequency that we found it at, which is found the same way as the transmitter. Once we demodulate that signal, it's going to be passed through a bandpass filter and then demodulated again in order to get the binary data from the signal we just received. So what are the advantages to using frequency hopping? So the first one that is difficult to intercept, interpret, or jam these signals, which is really important for such uses like military. So the reason it's so difficult is because to intercept this signal, the other device trying to receive this signal would have to know the channel sequence that the signal will hop through. And this is very difficult because another device might not have the same algorithm or might not be synced up to the same channel and seed value, and so it's a low probability that they would be able to intercept it. It would most likely just look kind of more like noise than anything. Then they also have a resistance they're resistant to interference. So the reason for this, that there's a low possibility that there will be interference, is because two different devices using two different random sequences would produce a very low probability that they'd be on the same channel at the same time. Due to the random sequence and different channels synced and the different algorithms, it's just a really low possibility that you'll randomly produce it where two signals are on the same channel at the same time. The disadvantages to using frequency hopping, though, is that there's a low transfer limit, and only so much information can be sent over any given frequency at a time. There is also no redundancy or error checking built into the system, so the system could potentially become unusable due to bad channels. And bad channels are just any channel that maybe didn't give a good signal back or has way too much interference on it. And so you usually would not want to use those, but since there's no error checking or redundancy built in, you won't be able to not use them. If it just comes up in the random sequence, you'll be going there. This can eventually make the system unusable, though, because you do have a set number of frequencies you'll use in a sequence, and so if a lot of them are bad channels, then that is going to definitely mess with your system. So now moving into the Bluetooth application. So Bluetooth uses frequency hopping, and it uses it in the 2.4 gigahertz band because that's the band that it is meant to be used in, and it will hop through the 79 channels allotted in that band. So Bluetooth is set up a little different because that it has a master-slave relationship. So as you can see, the block diagram is fairly similar to the other block diagram, but there is the added element of the clock. And the clock plays a pretty important role. So the master and the slave are synchronized. Again, this is a really important part. Frequency hopping doesn't happen unless the transmitter and the receiver are synchronized. And so they're synchronized using the master clock. So this is done by adding an offset to the slave's native clock. And this has to be updated regularly since the transmitter and the receiver aren't using a singular clock. Their clocks are just being synchronized together. So through this, you'll get that the time and frequency are going to be synchronized. Also is the master that is going to determine the unique channel pattern, which is pretty similar to how we saw it before. But the master will do this through its clock and through its Bluetooth address. And that's how it will control the unique channel pattern that we'll eventually come up with. So as you can see in the photo, again, pretty similar, gonna go through the same pseudo-random generator, frequency generator, and modulator, but again, the only difference is that there is a clock added on. So I'm going to deep dive a little more into the hopping pattern specifically for Bluetooth. So as I talked about before, with frequency hopping, you're going to have a unique and pseudo-random set of channels that you're going to go through. Here in Bluetooth, they're directly linked to the number of time slots used for data transmission. So Bluetooth transmission channels are split into time slots that are 625 microseconds each. What this means is that frequency hops can either be 1, 3, or 5 slots long. Now this does not mean that if you do 5 slots, you're going to have 5 frequency hops. It's just going to be 1 hop per slot length, regardless of if you're using 1, 3, or 5. So that is demonstrated over here in the picture where you can see the differences in the slot lengths. Another thing about the hopping pattern is that eventually the pseudo-random pattern generator for Bluetooth will repeat itself. They've approximated this to be 23.3 hours, which this is all based on that Bluetooth has a hop rate of about 1,600 hops per second. Furthermore, Bluetooth has a hop period, which is 2 to the 27 hops long, so fairly long, and this is really just to help to avoid accidental synchronization between different devices that are within range of each other. So it's just making sure that the master and the slave, or slaves that are connected to each other, are the ones that actually want to be connected to each other. So continuing to dive deep into Bluetooth, Bluetooth used to use normal frequency hopping that we've been talking about this whole time. But in around 2003, revision 1.2 came out, and this added adaptive frequency hopping to all Bluetooth devices. It made it kind of the standard. So adaptive frequency hopping is great. It allows the device to change the channel sequence to avoid bad channels. So as we talked about before, bad channels are those channels that have a lot of interference or maybe not giving back a great signal, and they're the ones that you would want to avoid. But before, with just normal frequency hopping, we couldn't avoid them. We were kind of stuck with them if it turns out that that was the frequency that was chosen for our hopping pattern. Now, adaptive frequency allows us to take that bad channel out of the running, so remove it from our sequence until it quote-unquote becomes a good channel again, so less interference, or just all of a sudden it gives a better signal. So this is really helpful when it comes to Bluetooth. So the master and the slaves in Bluetooth have the ability to monitor the channels for bad channels. And the reason it's not just the master that does it is it's because interference really depends on the device location and the transmitted power. So that way you just have a more accurate reading of the quality measurements when all are able to monitor the channels. The way they monitor this and really judge if a channel is good or bad is using just metrics, such as signal-to-noise ratio or packet or bit error rates. It'll look at that and decide from there. So again, this is really helpful with Bluetooth, because with Bluetooth you have to have a minimum of 20 channels that can be used as a hopping pattern. So again, this just makes sure that we're really using, if you're using the minimum number of channels, that you're using the best channels you can for your device. And so this also really helps to aid interference, not only from other devices to your device, therefore impacting your device, but also so that you don't interfere more with other people's devices. So overall, it just helps to avoid the interference issue even more than just normal frequency hopping did. And that concludes my presentation on frequency hopping. Going over the history of it, how it works, and a little bit into how it works with Bluetooth and even adaptive frequency hopping. So here are the sources that I used for this presentation. There's so much more out there if you'd like to research even further into this topic. Thank you for listening to my presentation on frequency hopping, and I hope you guys have a great rest of your day.